Greetings and welcome, friends. We're talking today about sum and product of roots. It turns out there's some special patterns or formulas related to our roots when I add them and when I multiply them. You might not remember what roots are, but roots are the same as x-intercepts and the same as zeros. Those are all somewhat synonymous with one another. You could also refer to your roots as the solutions of your quadratic equation, all sorts of stuff. So anyways, roots, let me show you this. If I was to graph a parabola, all right, this is no particular parabola. Let me draw maybe this one here. Bam, that's good enough. The roots we know are the x-intercepts, right? So those are my roots. So those points I'm going to refer to as S1, comma 0 and S2, comma 0. Let's see, S2, comma 0. All right, so S1 and S2 are going to be the x coordinates of my x-intercepts, okay? And I want to point out that S1 and S2, S1 you could also think of as being the opposite of b plus or minus, nope, plus the square root of b squared minus 4ac all over 2a. And S2 is going to be the opposite of b minus the square root of b squared minus 4ac all over 2a. So we've got both of these are going to represent our two different x-intercepts. Notice we have a positive and a negative. That's the plus or minus from the quadratic formula. Now, does anyone remember, this is just kind of a side note, I guess, what was the equation to calculate the x-coordinate of the vertex, h?
Minus b over 2a.
H was equal to negative b over 2a,
Yeah.
right? Look at this. Negative b over 2a gives you the kind of x-coordinate of the vertex as well as kind of your axis of symmetry, right? So I just want to point out that negative b over 2a is kind of the midpoint between your roots. And notice if I was to add this value, well technically it's this value, that would put me here. And if I was to subtract that value, that would put me here. And so that's why it's the same amount that I'm adding and subtracting from the axis of symmetry, giving me my two x-intercepts, because we knew that the x-intercepts would be mirror images of one another over the axis of symmetry. So that was just kind of a couple of little side things I wanted to point out. But knowing that these are equations to find our two roots is what I wanted to start with. So let's talk about the sum of roots. And I'm going to derive our formula. I'm not going to have you write down the derivation of it, but I am going to have us write down the formula once we get it. So S1 plus S2. So don't write this down, just follow along. Opposite of b plus the square root of b squared minus 4ac all over 2a. If I add that to the opposite of b minus the square root of b squared minus 4ac all over 2a. Well, look at, if I try to add these, what's the good news? They have common denominators. So I can just add their numerators over a common denominator. So that would look like negative b plus the square root of b squared minus 4ac. I'm going to be really sick of writing b squared minus 4ac, by the way, from this part of the video. And plus a negative is the same as minus b, and plus the negative is the same as minus b squared minus 4ac. All over, for real all over, look how all over this is. All over 2a, right? Now, what happens when I simplify this? I can combine my like terms up top. How many b's do I have? 2 of them, and they're negative. And what happens when I combine these guys? Because those happen to be like terms. Oh, wow, completely. Swing, swing, right? So all over 2a. And what happens there? What can I simplify? Right, is that what you were saying, Natalie, that the 2's cancel out? So I get that S1 plus S2 is equal to the opposite of B over A. And that's the sum of roots. That's the little pattern or formula that we've just derived for the sum of roots. So that's one of the little formulas we learned today. The other one is the product of roots. Actually, I guess I should start by writing that. Product of roots. Nope. That's fine. So here we go. S1 times S2. Nope, don't write that. I'm going to derive it again. I'm going to have the opposite of B plus the square root of B squared minus 4AC all over 2A. And I'm multiplying this by the opposite of B minus the square root of B squared minus 4AC all over 2A. Right? So I'm multiplying these. What happens when I multiply the denominators?
You double it, so it's like
4a squared. 2 times 2 is 4. A times a is a squared. And the numerators, does anyone notice anything special about my two numerators?
They are conjugates.
Those are conjugates. What? That is awesome. Right? Those aren't quite opposite, aren't quite the same. That's because they're conjugates. Remember their name. Wow, that was a great little song I just made up. And since those are conjugates, I know that a plus b times a minus b, the sum and difference of squares, is going to equal, does anyone know?
A squared minus B squared.
A squared minus b squared, difference of squares pattern. So, let's plug this in. So my a, oddly enough, is going to be negative b. That's weird, but okay. So negative b all squared minus b squared. B is going to be this whole square root. B squared minus 4ac in parentheses all squared. So let's simplify this. DJ, question. What is negative b all squared? Positive b squared, right? Because that minus sign being inside the parentheses, going to become positive. And, ooh, guys, what are your thoughts on this? Yeah, the square and the square root cancel out with each other. Ching, ching. Now, be super careful with this. This is where I made a mistake last class, and I didn't notice it for another like 5 minutes. When those cancel out, I've got minus this whole thing. Minus that whole thing. So I'm going to have to actually distribute this minus sign properly.
Oh, so you messed up pretty bad.
Yeah, a little bit. A little bit. B squared minus b squared. And what happens when I distribute this minus sign?
It turns positive P of
Exactly. Positive 4ac all over 4a squared. Okay, so let's see. Combine some like terms. What happens there? Swing, swing. Those cancel each other out. I get 4ac over 4a squared.
You can simplify by 4.
The 4's cancel out. And a to the first cancels out with one of those, leaving an a to the first. So I get S1 times S2 equals C over A. What do you know? So that is the formula for the product of roots. Why would I need that? That's a good question. We're going to show a couple benefits of this right now. And actually, sometimes people discover things about math not yet knowing what its need might be. And it's just interesting because it's true. But in this case, we actually do have some uses for it. What if I knew my x-intercepts, all right? So let's say I knew where I started and where I landed when I shot like an Angry Bird. And I wanted to find a quadratic equation that would represent that, or something like that. So starting with our x-intercepts, let's say find a quadratic equation. Why do I keep writing capital letters? Equation whose roots are the following. What if I have 3/4 and -12/5? Yeah. So notice I said a quadratic equation, not the quadratic equation, because I want to point out real quick, you don't have to write this part down, but if I have two particular x-intercepts that I'm shooting for, I could have a regularly shaped parabola that passes through those. I could also have a super steep parabola that passes through those. I could also have an upside down wide parabola that passes through those. It turns out there's infinitely many parabolas that pass through those two x-intercepts. So that's why we're finding a quadratic equation. And typically we'll find the one that has the nicest, simplest setup. So these are our roots. Now, question side note, these roots, all right, if those were the solutions to a quadratic equation, what must the discriminant have been? What type of discriminant? What kind of number would it have been?
Positive.
It would have been positive because I have two real solutions, and anybody?
And perfect square.
And it's a perfect square because these are rational numbers. Well done, Seymour. So now that I know these roots, I'm going to say, okay, one of these is S1, one of these is S2, and I'm going to find their sum and product. All right, so over here, let's find their sum. So S1 plus S2 is equal to 3/4 plus, or just minus 12/5, I guess. And in order to combine those, I need an LCD. LCD between 4 and 5 is 20. So this one I'd have to multiply by 5 over 5, and this one quattro over quattro. So this is going to equal 15/20 minus 48/20. And that, I believe, is -33/20. Now question, what was S1 plus S2 equal to?
Negative B over A.
Negative B over A.
So it means that your A is
Not guaranteed. It means that A could be 20 and B could be, well, actually, what would B have been?
33.
Just the 33, right? Because the opposite of B was -33. So plain old B would have been positive 33. So it's not guaranteed. All it does tell me is that the ratio of B over A, or negative B over A, is this. So maybe B and A are twice those values, or half those values, or 1,000 times those values. But they hold that ratio.
Now what we're going to guys are going to multiply S1 times S2.
Yeah, let's find their product as well. I like it. S1 times S2. Multiplying is easier than adding in the case of fractions. So let's see. I'm going to cancel some stuff out. Between 4 and 12, 4 goes into 4 once and into 12 thrice. And now I can multiply across. 3 times -3 is -9. And 1 times 5 is 5. And question, what was S1 times S2 the same as?
C over A.
C over A.
Oh, wow.
Now, all right, looking at this, notice my A's are in disagreement with each other for now. So what I'm going to do is multiply one of these to just get a common denominator, so I can just say A is whatever their common denominator would be. Okay? So what's the common denominator between 20 and 5? 20. So I'll multiply this one over here by 4 over 4. And I'll get negative 36 twentieths. And now that's got a common denominator, so I can just figure out my A, B, and C. So what would A have been? So A is 20. B would have been 33. And C is negative 36 because C was positive C, so it did have to have that minus sign. So that means my quadratic equation is going to be 20x squared plus 33x minus 36 equals 0. And that is a quadratic equation that has those roots. And if I wanted a variation of that, I could multiply it by 2 or divide by 7, and I would find all sorts of variations of other quadratics that have exactly the same roots. And if I wanted the equation, a quadratic function rather, that had those x-intercepts, I could just say y equals 20x squared plus 33x minus 36. All right, so let's do the same kind of problem, but with some different roots. So same setup, find a quadratic equation, I'll just summarize it this time, with roots. You guys are going to love this. You ready? 7 minus 3i and 7 plus 3i. What? So that means S1 is 7 minus 3i and S2 is 7 plus 3i. So this quadratic equation I'm looking for has imaginary or complex roots, more specifically, I guess. What does that mean the discriminant must have equaled? What kind of number?
Irrational.
A negative number as the discriminant tells me I will have 2 complex solutions or no real solutions. So that's what we got going on. So let's find the sum of these. S1 plus S2, 7 minus 3i plus 7 plus 3i. You can put that in parentheses there if you want it, but the plus sign's not going to distribute or nothing. So let's combine like terms. 7 plus 7, it's 14. And negative 3i and positive 3i. My favorite part, whooshing, whooshing, Fruit Ninja. Bam, right there. So I get 14. And what was S1 plus S2 the same as?
Negative B over A. Yeah.
Negative B over A.
A is 1.
That means A could be 1. Could be 1. Let's see. And let's similarly find their product. S1 times S2. 7 minus 3i times 7 plus 3i. Conjugates! That's right. So I'm going to use my pattern. I'll say A is equal to 7, B is equal to 3i. Different A and B than these ones. Man, those mathematicians really should have thought of some other letters. So I will have this equals A squared minus B squared. So 7 squared minus 3i squared. So that's 49 minus 9i squared. Ooh, I squared anyone?
Negative 1.
It's negative 1. 49 plus 9 is 58. And question, what is S1 times S2 supposed to be?
C over A.
C over A. So, based off of this information, my denominators both happen to be the same, so I don't have to manipulate it in any way. What do you think A, B, and C are?
A is 1. B is negative 14. And C is 58.
Correct. Right, and B, since the opposite of B was positive 14, regular B must have been negative 14. So now I can write my quadratic equation. X squared minus 14x plus 58 equals 0. So this is the most vanilla plain quadratic equation. It's got the most reduced coefficients, I guess. The smallest values of a, b, and c that are not fractions. All right, but I could have any multiple of this, and it would also have the same imaginary roots. Now, one last trick you can do with the S1 and S2s. Let's say I had the following that said solve and check. You can actually use them to check. All right, suppose I had this problem, x squared plus 9x plus 20 equals 0. And let's say I solved this. I would have, of course, factored it maybe, or completed the square, or quadratic formulaed it. I'd have an x with a 4 and an x with a 5 equals 0. I would have figured out their signs were both the same, and they were both positive because they added to be positive. And now, Natalie, would I say my answers were 4 and 5? Oh, right, because I'd got to set them equal to 0. Good move. Sure. All I really wanted to get to the point here was to get the answers. So that means those were my roots, or my x-intercepts, or my zeros. So this one is my S1, this one's my S2, right? Something like that. Now, let's check using our sum and product of roots formulas. So let's add these together. S1 plus S2. Negative 4 plus negative 5 is negative 9. And S1 plus S2 is the same as? Yep, they're always over A, which is nice. And let's multiply these guys. S1 times S2 would have been negative 4 times negative 5. So that's negative 20. Positive. Oh, good catch. Thank you. Nat Daddy with the save. And the product of the roots is supposed to be the same as C over A. So yeah, we could throw that over 1. So what would A, B, and C have been?
A is 1, B is 9, C is 12.
Opposite of B was negative 9, yep. And 1, 9, 20? 1, 9, 20. So it checks out. Now, if it didn't check out exactly, but what if this was 2, 18, and 40? I still would have been right. I would have been like, okay, I just would have, it's a multiple of those, and that's fine. So that's the idea. I mean, not too crazy of a lesson. I just undid my 20 there. Not too bad. Sum and product of roots. S1 plus S2 is negative B over A. S1 times S2, C over A. Just kind of a unique, neat little pattern that arose. And that's what mathematicians usually do. They tick away at things, they combine formulas, see what happens, if it's worth, having another way to represent stuff. And sometimes it is, sometimes it results in some cool shortcuts or whatever. So, thanks for watching, Internet friends. Bye-bye.